Hello everyone. Today we'll talk about the solution to the problem make sum divisible by p. So we want to remove some contiguous subarray from this given array, maybe not removing anything, such that the remaining array is divisible by p, and you want to remove as few elements as possible. So there are two things that you should probably start thinking about when seeing a problem like this. So the first more general thing is that if we want to remove some subarray, then by removing that subarray, of course, we will change the remainder of the remaining elements. And it might be useful when removing a subarray to know what the remainder of all the elements in that subarray is. And this is a very standard problem which can be solved with prefix sums, because as a reminder, when we have an array, we want to calculate, for instance, the sum, and in this case it's a sum modulo of some subarray, and you have pre-calculated values for all the prefixes, then you can just take the value for the prefix that ends at the end of our subarray and subtract the value of the prefix ending before the start of our subarray. So it's a simple problem to be able to get the sum, and in this case the remainder of the sum while dividing by p, of any subarray. Linear time preprocessing, constant time queries. So that is one thing. Another thing is that we want the remaining elements to be divisible by p. So, first of all, if the whole array, the sum of the whole array is already divisible by p, we don't have to do anything, right? Otherwise, we have to remove some subarray. So what do we know about that subarray? Well, if the sum of the whole array is not divisible by p, so it has some remainder r, then it's easy to notice that our subarray that we remove has to exactly have the same remainder r. Because we have, in a sense, r too much stuff out of alignment, so we have to remove exactly that much stuff. So now the problem transforms into finding the shortest subarray with the remainder equal to r. Okay, that's great. And we know how to look at a given subarray and say what its remainder is. So the final thing that we have to do is to decide how do we go about quickly determining what the shortest subarray is. And here we can use, for instance, the standard technique of moving one end of the subarray step by step in linear time then, and looking for, in this case, the closest other end to that end that we have fixed. So we can go through the whole array, and for every position of the right end, so maybe let me mark it as this, we'll find the rightmost left end that matches that right end. So how do we do that? Well, if we're for instance looking at the current right end at this position, then this prefix has some known remainder. So if we now put the start of our subarray at some position, what is the remainder of the whole subarray here? Well, as we know from the standard preprocessing, is the remainder of this minus the remainder of this. Since we want that subtraction to result in this value r, and our original value here is equal to, let's say, p, then it's easy to notice that we want exactly our current remainder, so p, minus the remainder of the whole array, so r, and of course all of this modulo p. And we want this subarray ending at this position to be as short as possible. So ideally we would like to have the information of what is the closest to us element on the left, such that the prefix ending before that element has the remainder equal to exactly this p minus r. And it's easy to calculate it. We can just essentially doing the same procedure as calculating those prefix XORs. We actually don't have to calculate them explicitly since we solved this problem in, well, this part of the problem in a single pass. Whenever we see a new prefix, so we'll be maintaining a running remainder, we just update that. Okay, so if here we have, let's say, some remainder q, then this is the rightmost position that we've currently seen of the remainder q. And that leads us to the full solution finally. So we'll be maintaining the position of the previous remainder for every possible remainder. First we calculate our target, so the starting remainder of the whole array, and if it's already 0 then we don't have to do anything. The length of the subarray that we have to remove is equal to 0. Otherwise we have to maintain a running remainder, and remember of course the best result. And now we enumerate our nums, so we have the index and value of every element in the nums. We add that element to the prefix remainder, take it modulo p, and of course our target now, as I mentioned, is the current remainder of the prefix minus the remainder of the whole array, modulo p. If we have already seen this target remainder, then we can subtract that prefix and get a good subarray that has the remainder equal to exactly r. And in that case it has length of our current index minus the index saved in our lookup dictionary for the value other. And of course it might be better than our best value, and of course now we have to remember that this is the rightmost position that we've seen our current remainder at. So we remember it in the prev dictionary. And at the end we return -1 if it was not possible to remove a correct subarray, otherwise we just return its length.